And then part 3. Okay, part 3. Part 3 suddenly said, oh, now I have another guy who's called Jn. Jn is integration from 0 to 1 xn bracket 1 minus xn dx. And it starts from 0 and then up to infinity. The question part 3 said, using the result of part 2 or otherwise, show that Jn is n factorial square over 2n plus 1 factorial. So if you look at this guy, maybe I go back to the picture that contains all the part, probably you can see the relation between part 3 and part 2, because the question said use the result from part 2. Use the result from part 2. Result in part 2, we have proved, okay, trying very hard to prove this guy. But you can see before that, before part 2, what is that? Before part 2 indeed is this guy, which is in part 1. So sometimes, when you watch the video, I hope you can kind of learn from my thought process, because if you watch other videos, maybe the teachers or the tutors would just simply demonstrate, oh, it should be like this. But I think sometimes we as a tutor should put ourselves into students' shoes, because sometimes it's not as easy as we thought, especially when we sit in the examination under the time pressure. Then how can we think of the question? I think you can look at the pattern here. Let me highlight in green. This guy. For the Jn, I think I reckoned that the Jn and the In is pretty similar. Similar in the sense that, especially for this one, the power. Okay, because the power can be splitted up into 2 parts, and also it is another guy Jn, and that's why the first thing that we should link it back is, does it correlate to In? And that's why if I do some adjustment for you, then probably you will see the relation. The Jn is something like this, the Jn. Okay, so in part 2, we know that In is 2 to the power of 2n and then n factorial square over 2n plus 1 factorial. And then In, Jn now is what? Now is integration from 0 to 1, and then xn, and then 1 minus xn dx. And at the same time, for the first part, In is what? In is integration from 0 to pi over 2 psi 2n plus 1, and then 2 theta d theta. If you can look at the pattern, if I want to change it back to the Jn form, isn't it I can do something like this, which is integration from 0 to pi over 2. So first of all, I can split it up, which is sine 2n 2 theta times sine 2 theta d theta. And then I want to put the n as the power, which is integration from 0 to pi over 2 sine 2 theta, and then square, and then whole bracket to the power of n, and then sine 2 theta d theta. And that's why you can see, at least I can form something like similar to the Jn, right? And that's why you can compare the pattern, which probably I will substitute what? I will substitute the x as sine square. Instead of 2 theta, I will just simply substitute as theta, because later the theta we can adjust for the boundaries. Okay, we can adjust for the boundaries. And that's why here you would just simply put x as sine square theta. And then dx will be 2 sine theta cosine theta d theta. And when x is 1, the theta is pi over 2. When the x is 0, the theta is 0. This is something called a change of variable, right? Change of variables. So indeed, for the substitution, this is just the first method that I can teach you, how to do it. But indeed, the explanation sometimes, I will tell the students how to observe this kind of substitution. Why we know that the x is sine square theta, and probably you have to attend my class or look at maybe later. I will post some videos to review the training on that part. But here, when we substitute the x as sine square, then we apply the change of variable to change the boundaries. And that's why the next step is pretty easy. The Jn, we can do some adjustment. The Jn, originally is what? Originally is 0 to pi over 2. And then this is sine square theta n. And then 1 minus sine square theta, and then n. Dx will be 2 sine theta cosine theta d theta. And so what is the next step? The next step is Jn. The Jn will be integration from 0 to pi over 2. So this is just sine 2n theta, and this is cosine square, and then times the power n, right? So 2n theta, and then still remember, what is this guy? This guy is your double angle formula, which is just simply sine 2 theta. Sine 2 theta d theta. And then the next step, if you have done enough practice for the HSC Extension 2, then probably you will know that you have to do some adjustment. Okay, what is the adjustment? Let me try to demonstrate. Like this. The adjustment is that you have to observe, this is sine something, cosine something. Indeed, we have to apply the double angle formula again, which is, this is 2, and then to the power of 2n. I have to multiply myself. But at the same time, I have to do the adjustment to cancel it out, like this. And then I will have something like Jn equals 1 over 2 to the power of 2n, integration from 0 to pi over 2. And then you can see I can take out the 2n as the power, which is 2 sine theta cosine theta 2n times sine 2 theta d theta. And then Jn will be 1 over 2 to the power of 2n, integration from 0 to pi over 2. Then this is sine 2n theta d theta. And Jn will be just simply 1 over 2 to the power of 2n, integration from 0 to pi over 2 sine 2n plus 1 2 theta d theta. Is this guy have any familiarity with it? This guy. This guy indeed is your IN. This guy's your IN. Miraculous. So this is your 1 over 2 to the power of 2n. Then what is your IN? Your IN is the is the stuff that you have proved in your part 2. So that means that it will be 2 to the power of 2n and n factorial square over 2n plus 1 factorial. So this is your in in your part 2. And that's why you can cancel out the 2 to the power of 2n. And that's why your Jn will be n factorial square over 2n plus 1 factorial. That's it for part 3. A very good question. Okay, so this is how we deduce from the part 2, and then look at the pattern of the sign that is similar. You find a similar pattern of the sine to theta, and then you substitute the x as the sine square theta. And that's why here, indeed, for the substitution, even without my guidance, I think like for those students who have done sufficient practice in the substitution part, they should be able to observe this. Okay. The last part. Okay, for the last part, the 2-mark said we have to prove that the 2n factorial bracket square is smaller than or equals to the bracket 2n plus 1 factorial. So indeed, like to me, this question is not an easy task, because like suddenly I can't think of why the starting point is like this. But later when I read the question more carefully, I think we can use the technique of backward deduction again. So we can start with what's been given by the expression. So backward deduction. So that means that I start with the given expression, which is 2n factorial square is less than or equals to 2n plus 1 factorial. And then I do some algebra, which I kind of like reverse the process, which I have 2 to the power of 2n, and then n factorial square is less than or equals to 2n plus 1 factorial. And then I can have n factorial square divided by 2n plus 1 factorial, which is less than or equals to 1 over 2 to the power of 2n. And I will have n factorial square over 2n plus 1 factorial, which is less than or equals to 1 over 4 to the power of n. So indeed, like, once I have got this number, then I will just think of what is the Jn that we have proved. The Jn that we have proved in part 3 is indeed like this one. This one is exactly the left-hand side of our inequality, which is the n factorial square over 2n plus 1 factorial. But what is the Jn? The Jn, if we look more carefully from part 3, indeed is the integration from 0 to 1, xn bracket 1 minus xn dx. So that means I can start from the Jn to see what's the correlation between the Jn and a 1 over 4. So the Jn will be integration from 0 to 1, and then xn 1 minus x to the power of n dx. So if I do some simplification, this one will be 0 to 1, and then this one will be negative x squared plus x to the power of n dx. Let's say if I presume this one is fx, so fx will be negative x squared plus x. If I derive this guy, this one will be negative 2x plus 1. And if I put the f dash x as 0, then that means that when x is 1/2, fx attains the stationary point. And this one should be maximum, because like if I further derive it, it will be negative 2, smaller than 0. So that means that what? When the x is 1/2, f 1/2 should be the maximum point. Let's see what is the maximum point. In this case, will be negative 1 over 4 plus 1 over 2. The maximum point is 1 over 4. So that means what? That means like indeed for this guy, I can prove that it must be smaller than or equals to the integration from 0 to 1 over 4 to the power of n dx, right? Because I have already proved that the maximum must be this guy. So if I really do the integration, so this one is just simply 1 over 4 n and then x. Substitute the x from 0 to 1. So that means that this guy will be just simply 1 over 4n. If that is the case, that means what? That means like the starting point must be correct. So that means like the step 1, I can start from here, and then I can go back to my perfect proof, starting from the first line here. And then that, if I have a top-down approach, then that will be a perfect proof of the inequality. So I think, the difficulty lies in the correlation, whether you can find that we have to start with the Jn, and then you have to know that the maximum of the fx is 1 over 4. If you can figure it out, then you can already solve the inequality starting from the first step. Okay, and that's it for the big boss question in that particular year, and I hope you enjoyed the video. And if you want to learn more from this channel, please like our videos and subscribe to our channel, and I will see you next time. Bye bye.